Risotto room. After that, welcome to Riccardo Magliocchetti that will talk us about simple serverless data pipeline.
Okay, hello everyone. Thank you for being here. So my name is Riccardo Magliocchetti, and today I'd like to talk to you about how to build a simple serverless data pipeline. First of all, I'm sorry, but I'm not that engineer. By trade, I'm backend engineer. So my goal for this project was to have a simple architecture, better if managed by someone else. And by someone else, I mean other companies and not my colleagues. And so the agenda for this talk, first we'll see an overview of this simple architecture for a serverless data pipeline. Then we'll see a description of the data lake we used, which is comprised of AWS S3, AWS Glue, and AWS Athena. Then we'll take a look at Apache Superset, which is the exploration and the visualization platform we used. Then we'll discuss a bit about data formats. And finally, we'll talk a bit about vendor locking. So let's take a look at the architecture. You can see the graph here. So on the left, we have our application, our Python application, of course. In my case, it was a Django monolith. The application, see the arrow, pushes the data to the data lake, and pushing the data out instead of having someone pulling is, in my opinion, make things a lot simpler. In this case, it was even simpler because the application already was using S3 for storage. So let's take a look at the data lake. First, we have AWS S3 that we use as storage to store the files uploaded by the application. Then we have Glue, which is a AWS service that is used to map the content we put on S3 to a collection of data. Imagine that is, in the end, it's like a database table. At the end of the data lake, we have Athena, which is an AWS service that let us query the data we have on the Glue in SQL. For newbies like me, a data lake is simply the place where you store and process your data. At the end of the pipeline, we have Apache Superset, which again is our visualization and exploration platform. So let me talk about a bit about the context in which this architecture was developed. The team was small, and there weren't any data engineer on the team. Especially there weren't anyone that could take care of the pipeline as a job. The end users of this pipeline are not data scientists or other engineers, are business people. So we need a tool that can be used by business people. Fortunately, this is not a real-time data pipeline because we don't have any real-time requirements. And so the data, to make things simple again, is generated once a day. More importantly, we don't generate much data, which is another important metric. We are talking about megabytes of compressed data generated per year. Still, I think this may be interesting for people that works in a small team or small companies. This, of course, was not something that I've done by myself. It's a team effort. So I'd like to thank you, Nicola Martino, for his AWS knowledge, and Bartolo Albanese, who helped me define the data to extract and create all the setup on Apache Superset. Now let's dig a bit more on the data lake. So first a recap. Again, the data lake is comprised of S3 to store our files pushed by the application. We have Glue in the middle to map the content of these files to a collection of data, sort of a database table. And then we have Athena to being able to query this data in SQL. Okay, now let's see the single components. First, S3 is a cloud object storage. If you're not familiar with the term or the concept, imagine being it persistent cache, a big persistent cache that looks like file system. It's quite cheap to run, but as always on AWS, you have to be very careful about the data transfers you do from and to AWS or the internet. Every cloud platform, if you're not using AWS, offers a comparable or even a compatible service. So not much of a lock-in. Then the second service is AWS Glue, which is a serverless data integration service. Being serverless, you pay by the use. And if you're not an heavy user, it's very cheap. We are not doing any transformation of the data once we store it on S3. But if you need to, if you require any cleaning or transformation, aggregation, whatever, you can do here in Glue. You can choose to use very own interface, which is based on Apache Spark, so you can use the PySpark libraries. Or you can cook something yourself. For example, you can, use the Lambdas, which are the AWS serverless computing service. So maybe you can listen to the S3 bucket events. So when you upload a file, you can bring up the Lambdas, let them process your data and store them on another bucket. So in the end, the only functionality we use in Glue is the data catalog functionality, which is the visibility to map the data from the files stored on S3 to something that looks like a database table. So it works like we upload the files on an S3 bucket. An S3 bucket, consider it like a directory. And Glue will take care of aggregate all the data and present them as a single table. So at the end of the data lake, we have Athena, which is a serverless query service. That means that it lets you query in SQL this data stored in S3 and exposed by Glue. This is the interface that Apache Superset is using to connect. Speaking about pricing, it costs about $5 per data queried $5 for terabyte queried from Glue. So this was our data lake, and at the end of our data pipeline, we have Apache Superset. Apache Superset is a data exploration and visualization platform. It's written in Python using the Flask framework. Data is accessed via SQL Alchemy and loaded into Pandas data frames. And the charts are rendered in JavaScript. It can connect to plenty of databases. At the time of writing these slides, there were around 40 supported databases. And as long as you have a working SQL Alchemy dialect, you can use it as a data source. The platform also offers a SQL editor, so you can run your own query just to take a look at the data or experiment. In our case, we used an hosted version from Preset, which is the company that employs most of the Apache Superset developers, and so it stewards the project on Apache. So let's see some concepts in Apache Superset. So first, you have to configure a database, one or more database, to retrieve your data. And then, once you've done that, you can choose which database table to expose to the users of Apache Superset. And these exposed database tables, are called datasets. Once you have datasets, you can create charts using the data of a single dataset. And the chart is just a visualization applied to a dataset. So in the screenshot, you can see a graph. The results of the query at the bottom of the picture. and then the fields that was selected to create it. We won't dig into any data, but in case you have questions. Once you have your charts, you can assemble them in dashboards. And on the picture, you see on the right all the charts. And on the left, you have a filter where you can filter all the data that is powering the charts. So you change the filter, and the charts updates. Finally, we have the built-in SQL editor, which is called SQL Lab. This is a tool that permits you to write your own SQL, as you see on top right. You can see the past queries, and on the left, you can see the data you're querying. So, the database table, the dataset you're querying. And so, now it's time for discussing a bit about data formats. So, our first implementation, we used CSV files for simplicity. It's text, and so it's easy to debug, and it's easy because you can use your favorite CLI tools. You can use grep, head, tail, whatever. Or even better, for debugging, you can load them on a spreadsheet. I think it's priceless for debugging data export issue. At least it was for me. Problem is, it's not space efficient. So we moved to another format where we started with ORC or ORC. I don't know how it's pronounced. Anyway, it's a binary columnar format. Being columnar, it means when you query, you don't have to parse all the files, and so you can discard the data you don't need, the columns you don't need. Being compressed, files are a lot smaller, smaller to store, and so cheaper to store, and then faster to query. If you remember, Athena is paid by the terabyte you read, so the less data you store, the less data you read, the less you pay. Problem with ORC or ORC is that the tooling is, at least the tooling I find, the CLI tools I find, are written in Java, which is not our preferred tools to have around, and we were uncomfortable to use these jars found on the internet. And so we changed the format. We moved to Parquet, which is again another binary columnar format. That, on the other hand, has more CLI implementation. There are at least Python and Rust implementation for CLI tools. In our test, the Parquet files were 15% bigger than our C file, but we are happy to pay the price because it was a lot better for developer experience. Also, Parquet has a way bigger ecosystem. It's using interesting projects like Apache Arrow, which is an in-memory columnar format, and Alessandro Molina will give a talk this afternoon, I think. Also, another interesting project that is interoperable with Parquet files is DuckDB, which is an embeddable analytical database. Think of like SQLite, but for analytical workloads. Finally, let me talk a bit about the vendor locking. This solution is based on AWS, and not because I have tons of AWS credits. It's not a sponsored talk, anyway. Because the company was already using AWS, so it made no sense to do something else. And so this architecture is tied to AWS service offering. Still, I think every other cloud provider probably has a different take on how they want you to run your data workloads or to run your data architecture projects. So, for example, if we would have used Google Cloud Platform, probably we would have used BigQuery, because I think it's preferred tools on Google platforms. Still, speaking about lock-in, if you have time and money to handle different infrastructure yourself, you can probably replicate all of this using only open source projects. So you can use Min.io as an alternative for S3 as a cloud storage. You can then use Apache Hive or whatever other Apache project that implements the same functionality there is to ingest the data from the object storage and provide something that Apache Superset can connect to, and Apache Superset as a connector for Hive. And of course, you can host Apache Superset yourself. So, conclusion. To conclude, I think there are tools out there that permits a small team or even solo developers to create cheaply some serverless data pipeline and without much operation overhead. I think it's particularly interesting for small teams or teams without data-specific roles. So if you don't have any full-time data engineer team, I think it's a nice platform. And so, again, in my opinion, serverless makes a lot of sense for a small-scale project. At least for me at least. Debatable, as always. I'll leave you a couple of references. The first link is the AWS idea of data architecture. As you can see, the idea consists of a ton of services, but you can choose only what you need. Then I leave you a blog post from Preset on how to set up Apache Superset connecting to AWS Athena. We have done things a bit differently because they used a dynamic crawler to update the data, but we did a static mapping, and so our solution is, costs zero money, so it's even cheaper. And finally, the superset documentation, if you have any interest in superset. So, thank a lot. That was all for me. I'm glad to take any question you have. Thank you.
Thank you. We have 3 questions. First one, why did you choose Apache Superset over other BI tools like Tableau or Power BI?
I mean, I have a long history with Apache Superset. Maybe, like, I've been using Apache Superset and contributing to Apache Superset since 2016, when it was very new. So just habit, I think. So I don't have a better answer.
Can you please repeat
the mic? I don't think it's working. I can repeat the question.
No.
No. Try.
Can you please repeat the name of analytical database similar to SQLite you mentioned? Thanks.
Okay, it's DuckDB. Duck, like the one that works.
Do you have any advice on automating testing of such pipeline?
Oh. But in our case, we do most of our testing on when we export stuff, and we kind of assume that the AWS still works fine. So we are testing that the data we export is what we expect. But being all managed services, I tend to trust AWS on this. So, not a great answer, but again, since the data is small, we can find problems very easily. So that's it.
Does AWS Glue modify the data in S3 or created replicas?
Well, data S3, I think that when you store data on S3, it's at least replicated in 3 times in storage, like in some servers. But it doesn't change the data. I mean, I think it's stored, how do you say in English? It's encrypted, but other than that, we don't change the data.
Perfect. How are you handling data transfer fees with the whole solution?
So we are lucky that you have not much data, and so the fees are manageable. If we would have a bigger amount of data, I don't think that I would have used S3. And speaking of S3, just an anecdotal story. We did have a tons of data, a lot of big files, 100 megs for each files on S3. We used CloudFront on front as a CDN. And still, with a CDN in front, the data transfer fees to the outside were a ton of money. And we moved to a fixed service like a DigitalOcean one for stored data. So I don't have an answer. The answer for me is, or you are rich, you can pay, or you move outside. Because I don't know how one can manage to pay a lot of transfer fees that other platforms don't have you pay.
How do you distribute to the business your interactive visualizations directly in Superset or integrated into web page?
No, the business people log into Apache Superset and use Superset. I think they're a bit advanced user. Some of them may know maybe a bit of SQL or can poke with the charts building, so they can dig a bit on the platform.
Are you receiving many files during the day and you schedule the pipeline once a day, or you get source data on daily basis and use trigger feature to start it?
Now we upload to S3 once a day, and Glue take care of everything, so we don't have to trigger anything. It works like automatically. So once you upload on a specific bucket, on the specific bucket you configured, you're fine. You just to have to do it once.
What's the role of Glue in your pipeline? Do you use it to infer the schema, or you use it to do some ETL before squaring?
We don't do any ETL, any transformation. And the schema, we map it manually once we start exporting the data. So its role is just mapping the data from S3 bucket to a file, to Parquet files in a S3 bucket, to something that looks like a database table to Athena and then Superset.
How would this architecture be reshaped in case of a real-time use case?
Oh. I probably don't use anything like that. But I don't have an answer that can satisfy who asked the question, I guess.
We have still 5 minutes. There are no more questions on Slido. Any question here in the room?
As a follow-up, okay, you can hear me. As a follow-up, you mentioned that you could use events for files being added to S3. Do you actually use it in your pipeline? Okay.
No, we don't use any event notification from S3.
Do you have any experience with it in other projects, namely about the consistency of it? Is it something that you can rely on, or?
I'm thinking if you're using something else, I don't think so. So sorry, can't answer.
No, worth asking. Thank you.
No more question?
Okay, thank you. Grazie.
Di domande.
Infatti,
Non te l'ho passato perché è un po' un'applicazione per i review, devo vedere se mi fanno qualche domanda del
quando
cazzo.
avevi parlato non
perché-
si sentiva il microfono, poi è partito. quindi-
Sì, sì. Just a quick announcement. Please use Slido to ask question. You can go on the schedule, and there is a ask question. Click, and will open directly on the Risotto room. And after that, welcome Dan Weldon, and we'll talk about serverless from scratch with CI/CD.
Wow. Cool. Thank you very much. So yes, you can hear me. That's great. So yeah, like I said, my talk today is serverless from scratch with CI and CD on AWS. It's a lot easier than you think, and mostly free. Or an alternative title would be to say serverless from scratch with Terraform. And it's Terraform that I'm going to be talking about and introducing today as well. As a little bit of a background to who I am and why I'm stood here. So, like I said, my name's Don Weldon. I'm a software engineer from central London. And I was actually, I was here at this conference last year, and I used this very slide to give you an idea of the technologies that I use, and also to just say how absolutely bonkers the UK was about 12 months or so ago. Since then, it's gotten a lot worse. I was making a joke about this Prime Minister. We've had 3 more Prime Ministers, or no, another 2 Prime Ministers since then, so that's 3. And another monarch as well. So it's just nice to be in Italy, really, a country that has less dramatic politics, you know. So, but no, so thank you again also to the organisers for putting on this conference today. It really is a lot of work to put on an event like this, and you really can't appreciate all the staff, volunteers, organisers, everyone enough. So a little bit more background about who I am. I worked for a long time for this company, Decision Lab, they're a mathematical modelling consultancy. I still have a little bit of involvement with them as kind of an advisor and associate. But I'm a contractor, an independent contractor, and I'm currently working for a City of London financial services organisation that I've chosen mysteriously not to name, not for any particular reason other than the fact that I'm not doing this in like a work capacity. This is just a bit of fun in Florence talking about Python. And I am apparently an expert software engineer at this large organisation, if you believe Microsoft Teams, which is a lie. So, I should clarify as well what I mean from scratch here. So we're saying serverless from scratch. What does from scratch mean? And I realised there was scope for ambiguity there. You could get confused. And I'm not talking about Scratch, the kids' programming language here. It's not Scratch in AWS. That's not what today's about. I'm sorry, you can leave now if you want. But it's not. That's not the purpose there. So from scratch, just as a bit in case people don't realise, scratch in English is to like scratch an itch. You can also have scratches, like on a table, if your dog is, well, my dog does that, definitely. So from scratch is a term originated apparently in the 1700s when they would start races from a scratch on the ground. It just means from the very beginning. So serverless kind of from the ground up, from the very beginning is what we mean. Should also say, what do we mean by serverless? Because fundamentally, all code has to run somewhere if well, you hope your code runs somewhere, probably. You want it to. So there's always a server. So what do we mean by serverless? So to give you a little history, my background is in part as a historian, so I can't resist it. But arguably the first ever internet server was turned on the 29th of October 1969 by not this guy's graduate student, Leonard Kleinrock. And the internet was a much simpler place back then because there were only 4 servers and they all looked like this. Move forward, say 20-odd years, 20, 30 years, you get the proliferation of home and office computing. And so servers start to look like this. They live in the corner of offices, and there are IT people that look after them and people that turn them off accidentally and end up losing weeks of work, that kind of thing. Fast forward a bit further into the early 2000s, and this is my first ever web host, poundhost.com, who were selling me basically £1 a megabyte web hosting, which was a bargain back then. And you've got there are companies that operate physical servers and resell them on for a tidy profit at the time. Fast forward a bit further, 2004, and then, well, properly 2006, when AWS launches with EC2, you've got this first idea of cheap cloud compute resources that are available in the cloud. Fast forward even further, you get to kind of Docker in 2013 and containerization and this idea that rather than managing servers to do your code and run your workloads for you, you start managing containers, and containers are going to controlled small environments that run on a bigger server like a hypervisor. A year later, Amazon launches Lambda, and it took a little while for it to, arguably, to catch on. And the idea here is that rather than worrying about a container, you're actually just worrying about a function. So developers write a function, and that function fires in response to an event. And so that's kind of what we, when people started to talk about serverless applications and the kind of technologies that go around that. So you can kind of see how we've gone from developers managing hardware down in the bottom to developers managing functions and functions as a service, or funtainers is a term that I've never managed to get to catch on at work, unfortunately. But so we can see how we're kind of moving up the stack and getting into more sophisticated worlds where we don't have to worry about managing base infrastructure. But that comes at the same time as the DevOps movement. So we've got kind of serverless and functions as a service where we just write code. But we also have this developer operations model where we say that developers are responsible for making sure that their services and their code also run. We don't have an ops team and a devs team. We have both developer operations. And now you get into this term DevSecOps, and think about how you can run that in a serverless model. But it means that rather than worrying about hardware and making sure that our servers are turned on and they're working and they're healthy and so on, now developers, we have to start worrying about all sorts of other things, because even a very simple resource or application will have lots of different associated little bits and pieces that you have to worry about in the cloud. So serverless doesn't mean that devs aren't responsible for managing servers. There's also quite a lot that we have to manage still. So these things might be IAM roles, secrets, deployment pipelines, CI/CD, and so on. So we've got some frameworks that started to emerge to deal with that. I think the first one that I ever used was Zapper, if people remember. It's still going as a project, but it was a tool, or is a tool, which will kind of auto-magically turn your Flask app or your Fast API application into a web API that runs in AWS. And you've also got the serverless framework here, which is a much bigger one, albeit perhaps a little bit more focused on JavaScript developers. But that said, it's not always possible to use a framework. Frameworks are often very good things, but if you're in a highly regulated environment, or you're behind some kind of bizarre proxy where you're not really able to use third parties, or you have some other strange rule inside your organization that means that for some reason you have to write your code to a particular fashion or standard, or it has to be in-house and so on, you're not always able to use that. And so I think that as a developer, understanding how to build things from scratch is important, it's useful. It's not what you want to do for everything that you build, but it is important to know and to kind of explore and have fun with. So what we'll cover today is a comparison of how serverless works compared to my laptop, when we're looking at a base example here, Fast API. I want to introduce Terraform, talk about what Terraform is, why you should use it and how it works, and also say, with a little caveat at the end, why frameworks are still good things, really. I should say this is the first time I've actually given this talk, so obviously it's going to be rough around the edges and feedback and so on, so I appreciate it there. So let's crack on quickly. Our example is going to be Hello World in Fast API. Hopefully, I'm sure most people are familiar with it, or if not, then it's a really great framework. You should use it. And Fast API, you see here, we create a Fast API application, have a single root, and run it. If we look at the docs inside of for Fast API, you can see here the recommendation is to use Uvicorn to run your application. And you can see, so I'm just running this application on my laptop here. And just a very quick shout out there, you can see I'm actually using PDM. Has anyone come across PDM yet? Good stuff, yeah. And it's a brilliant, it's an alternative to Poetry, brilliant open source dependency manager. Definitely check it out, it's really good. So yeah, we're running Uvicorn with PDM. And lo and behold, I go to port 8000 on my own laptop, and I've got my response just as we had there. It's worth thinking what just actually happened there. So to elucidate this, we'll use curl, which is a command line utility, curl, to make requests to our server. And so if we use it in verbose mode here, you can see that curl opened a connection. It sent an HTTP request. There was a response sent, and curl received that response. And you can see that that response there has been tagged by Uvicorn, the server that we were using to run the code before. And we can then get the content from our function as well. So what we just did was turned an HTTP request in my browser or in curl ultimately to a call to that hello world function. And there's a lot of things that have to happen to make that happen, because obviously my laptop, it opens a connection to a network, and that's not a Python call. That doesn't have any information about Python or what we want in it. So lots of things have to happen in the middle. And the important part of this is something called ASGI, or the Asynchronous Server Gateway Interface, which is what Starlet and FastAPI are kind of built around. So if we were to look at that very quickly in a diagram, and let's make a comparison between what will happen on my laptop and what will happen in the serverless cloud. So first off, on the laptop, we've got the HTTP client that makes the request, in this case curl. It travels across a network, which in my case is just the loopback interface on my laptop. There's a server that's listening, which is Uvicorn. It turns it into an ASGI object. It turns the request into an ASGI object, and then passes everything on to FastAPI so that it gets called. In serverless land, things are going to be a bit different, because we're using FastAPI still in serverless, which is it's an opinionated choice. But what we're going to have to do is, again, we make a request using whatever browser. We cross the internet. There's a server that's listening, and this is our first AWS resource that we look at. And that server is API Gateway, which I'm sure is a service that many people who've worked with AWS have heard of. And then this is where it gets a little bit different, because rather than calling our Lambda function with an ASGI object like we want for FastAPI, it gets called with something called this API Gateway Proxy Event, version 2. And that proxy event is passed to us by this integration, an API Gateway integration, which is a component inside of AWS. And then we have to use this library mangum, which irritatingly doesn't have a logo. So that's a shame for my diagram. But we use this library mangum, which does the translation for us. And then I should say that this diagram works in the opposite direction as well. So the response that we get from FastAPI will be translated by mangum, which will then go to API Gateway, which will then go back to the internet and to our browser. So if we look at where all of this code's happening, this part here, the mangum transformation and FastAPI, that's happening inside of our Lambda function. Whereas the API Gateway and the API Gateway integration, we kind of need a way of managing that currently. We can't just build that in Python. Well, that's not true, we can, but we're not going to here. So let's think about how we're going to, what the thing that we're going to build, what's it going to roughly look like? We're going to have our API Gateway that's going to be listening for our requests. We're going to have the integration that's going to then fire all of our requests to our Lambda function. But obviously, we're going to want to keep our code somewhere. Let's put it in GitHub. Is that me, or is that... do we know? OK, that's definitely me. Let's figure that out. If you give me one moment, sorry. Screen, Okay. Mirror. Apply. Let's see, everyone, which operating system I like to use there. Great. Are we? Tell you what. Let's do it like this. OK, there we go. So let's think about what does our ideal cloud setup look like. We've got API Gateway. We've got our integration that we discussed before. We've got the Lambda function. But obviously, we're going to want to keep our code somewhere. And that somewhere is going to be GitHub. We'll probably want to have a pipeline that sort of checks that any changes that we make are going to be working and sensible. We're going to then create a Docker image that we'll be using to power our Lambda function. And so that's roughly what we'll be looking like there. That's getting a little bit complicated already as a pipeline. There are going to be lots of individual resources that are managed each as a part of that pipeline. So first off, let's think about some of the changes we might need to make in Python. Well, these are actually very simple. We import that mangum library that I mentioned to you before, and then we kind of wrap the application with mangum. And then also we have to, because of a quirk of how API Gateway works, we're going to be adding a little prefix to all of our requests. So we have to tell this is unusual. Okay, we seem to be working. Are we got these connections? I'm not sure. Okay, so yeah, so we need to tell Fast API that that's the case there. Do we know anything about? So we've got. I think there's a problem in some other rooms as well. So we'll persevere. We'll see what we do. Okay, so these are all the changes that we need to make to our Python code. I wish I knew what my next slide was. I really need that. I really need that little trigger in my brain to know what to say here. That's helpful, isn't it? Okay, so yeah, well, so we need to get building inside of the cloud. And so the first thing that we might be tempted to do is to load up the console and start to think we've got a completely blank AWS account there. Brilliant metaphor. And we can start to think about doing what we call click ops, which is where you do a load of changes inside of the console, build the stuff that you want, and then hope that nothing changes, because why would it ever change? However, even for small projects, that's probably quite a bad idea. Setting up resources inside of the console and just clicking around and using a web form. It's great for quick exploration and some rapid prototyping. But once you get lots of resources working together, it becomes very difficult to manage your code properly. Cloud applications really consist of like a big, really highly interconnected graph of lots of different things, lots of different resources. And we need a way of making sense of those connections that exist between them. So infrastructure as code is an approach that allows us to do this, where we define all of our infrastructure, surprisingly enough, as code. And then we're able to sort of apply that code to our environments. Terraform, I would argue, is one of the best tools for doing this currently. So as a little introduction to Terraform, we write configs using HCL, which is called HashiCorp language. It's a declarative language that's used by Terraform and a few other organizations. And then Terraform, crucially, compares the config that we've said we want to what the situation actually is in our environment, in our cloud. And then it works out a plan to take us from where we are currently to the config that we want. And then if you're happy with that plan, you can approve that plan, and then Terraform will go and make all of those changes for you. If that plan doesn't make sense, Terraform will tell you that, or if there's a bug or something is wrong, Terraform will flag that for you in advance. So it really allows us to make changes to infrastructure with a lot of confidence, and really allows managing dependencies between resources. So say you've got 6 or 7 different resources that rely on one another in a chain. Terraform will work that out for you, will work out how that exists in the graph, and will make a plan accordingly. So this is kind of a really important thing to flag as well, in that cloud resources aren't pets. They're things that we need to be able to create quickly, destroy quickly, refashion. If you say, I want to suddenly fire up 200 Lambda functions and then delete them all, that's really the approach that we want for our cloud infrastructure. We want to be able to rapidly change it and kind of reason about it in a sensible fashion, not sort of be worried that if we tweak the server in the wrong way, suddenly all of our production stuff will crash. Pardon me. So, moving on. We can have a little look at some Terraform code now. Just briefly about Terraform, it's a CLI application. It's written in Go. It's open source. I mean, or at least most of the providers are open source, and you can install it using either a single binary or tools like TFN, which is like equivalent to PyEnd. It's not just an AWS tool. You can use it for dozens or hundreds, really, of different cloud providers. And if you want to, say, make changes in AWS that then get reflected in Circle CI and so on, you can do that very easily. There are 4 real key commands inside of Terraform: init, plan, apply, and destroy. And these are the 4 that you're more likely to use at any particular time. And I think you can kind of work out what each of them does. Pardon me, sorry, it's a bad time to cough, isn't it? That's better, sorry, thank you. So yeah, Terraform is modular. It works on a directory. So by convention here, for example, this is a minimal sort of Terraform module on the right-hand side. All it does is create an Amazon S3 bucket. By convention, we put them into 3 different files, but we don't have to. Terraform will just look for all of the Terraform files when you run it. And yeah, this, if we were to apply this, it would create an Amazon S3 bucket for us and have some outputs and some inputs. Crucially, we could then use that module as a kind of repeatable unit. Pardon me, sorry. my throat is, I swallowed something the wrong way. Yeah, we can use that module a little bit like a function for repeatable infrastructure in the future. So this is really useful because it allows us to make the connections between the different resources that we're creating really, really explicit. So if you think for our API gateway that we're going to create, or that we want to create, we've got several different resources here. We need to create, first of all, an API. We need to create a domain name for it. We need to create a route that we're going to proxy all of our requests to. We need to make the integration that we've discussed. And then we also need to deploy that to a particular stage. So that's 5 different screens inside of the console, which is a lot of clicking around. And if you realize at one point you want to change the name of one thing, say, and work something out, that's going to be a bit of a nightmare. So the Terraform approach here is there are actually 2 different Terraform configs here. One would run in a kind of global environment, and the other one would run inside of a kind of per environment, inside of CI sort of environment. But you can see here we've got several different resources that we're creating, but then we can crucially reference the properties of different resources in different parts of our infrastructure. So you can see some of these arrows here are references between different resources. And so, for example, we'll create a Lambda function, which isn't on here, but then we can use the name of that Lambda function inside of our integration, for example. And we can take the ID of the API that we create and use that elsewhere inside of our config. So we can also do like lots of kind of logic inside of and kind of processing like for each and creating various different variables and so on, just like in Python. Yeah, exactly, the syntax there. It does require a little bit of config because Terraform stores something called state, which is a representation of how your infrastructure was at the last apply. And to do that, we generally use an S3 bucket. It's not essential, but it's the most common one inside of AWS. So that does mean that there's a manual step here to create an S3 bucket. So kind of the message here, Terraform is great for building small, modular, kind of repeatable units of infrastructure and so on. And if we look at the example pipeline that we want to create here, you can see that we'd probably have one repeatable unit. So we'd have one kind of global setup here, and then one more repeatable unit that we'd do per environment, say for dev, prod, feature branches, and that kind of thing. So we can achieve that quite easily using CI and CD. Now, there's far too much code in kind of an example repo from scratch to go over in a talk, and I don't want to go through each part of that code. But I do want to flag your attention to kind of the fact that I swallowed some water the wrong way, apparently. I do want to flag your attention to this repository, which is on my GitHub. It's just been made public. There will be tweaks to it and a bit more documentation that's put through. But you can see some of the things that it'll create inside of here. You've got some of the initial variables for how that setup works. You can initialize it. You can run a Terraform apply to build some resources, create some things inside of Circle CI, and manage your secrets and so on, and create an API. Now, I'm dashing through this for a reason, and that is the title of this talk was, or is officially, Serverless CI, where serverless from scratch, CI and CD on AWS. It's easier than you think, and mostly free. And the mostly free thing is definitely true, but I would like you to come to my blame-free retrospective, which is that the it's easier than you kind of think aspect is not necessarily quite true. So this talk is intended as a kind of synthesis of lots of work that I've done over the last few years, and kind of to spread some enthusiasm about Terraform in the Python community. So I can say that there is a Terraform repo that you can inspect and look at there. It's just not quite 100% working yet because there is a very pesky little bug that I've discovered, which means that unfortunately I can't give the sweeping live code demo where we fire all of this up just now. But if you check my Twitter, I think over the next day or so, certainly as I'm at the conference, that repo will become sort of ready for you to check out and just run kind of make setup and see how things go. So yeah, conclusions, it's easier than you think. It's not always true, as you say, but understanding how serverless works from first principles is important for developers. And IAC tools like Terraform are particularly useful in developing this kind of understanding. So thank you very much.
Thank you.
Thank you.
We have some questions. Does Mangan affect performance, or is it only an AWS wrapper of UV kernel?
Of what, sorry?
Is an AWS wrapper of UV kernel?
No, so it's different. It does a different job to Uvicorn because it does a different transformation. But the cost in terms of doing that transformation per Lambda is negligible. It's I mean, Mangan's great because it's very well tested and like bulletproof from a kind of standards point of view. But the job it actually does is really straightforward. It takes one JSON object and then basically turns it into another. So it does that very, very quickly. So.
How easy is to create a custom Terraform resource from a Pythonista point of view?
Not that hard, really. I mean, so Terraform is not a kind of, my DevOps friends will kill me now if I say, but Terraform is not a particularly difficult language to learn. There are certainly some quirks and oddities to it, but it's well worth the kind of the overhead in terms of actually kind of working and learning it. Creating a module, yeah, you can do it in a matter of minutes. More complicated modules and so on will take longer, and there is definitely an art to it, but it's worth learning, I would say.
What is the difference between Terraform and AWS CDK? Why should I use one over the other?
Yeah, so CDK is essentially well, CDK and Pulumi are probably the two big alternatives to Terraform. My personal preference goes to Terraform because it's more agnostic from the AWS cloud, and it doesn't rely on using JavaScript. It's an entirely declarative language. That is an absolute pain sometimes when you want to use something that's a bit more logical. Would require a little bit of logic that you can do very quickly in JavaScript, say, but requires like 15 lines of Terraform. But that's edge cases. In my opinion, Terraform is definitely the nicer language to work with, and it's better. But if you need to do something in CDK, you can run CDK as a part of Terraform. So there's a way to plug that in.
How are you managing API gateway response and error schemas from Terraform?
So that depends. So in this example repo, I'm not put error alerting in and all that kind of stuff. In my financial services job, obviously we do pay a lot of attention to that kind of stuff, and we have dead letter queues for error requests and all sorts of stuff. But the point here for this example repo is that if you're starting to care about monitoring failure rates and sort of have a very high loads and stuff, then don't use this repo as your starting point. But this is definitely a kind of a gateway into learning about those things. So, great. Thank you very much.
Thank you very much.
Thanks. No, sorry for Yeah. Suddenly, swallowing
the schedule for clicking on this talk. And with further ado, welcome Sebastian Witowski. Okay, he will talk about optimizing your CI pipelines.
Thank you. Still need the microphone though, so hold your horses for a moment. No worries. Is it on? Can you hear me? Okay, you can hear me. Perfect. We're getting somewhere. Will my clicker work? It will be pity if it. Yeah. Up. Okay. Can I? Oh, okay. Where did my. Hey, come on. Stop creating separate screens. It's fun. Ooh, I lost my mouse. Come on, mouse. All right. Okay, we can get somewhere. And we already lost some time. Let's go. Hi, so my name is Sebastian Witowski, and today I want to talk with you about continuous integration, or to be more specific, about optimizing your CI pipelines. Don't do this to me. Yeah, I know, I was here. I'm not as good as having a small talk while the screen doesn't work as the previous guy. Let's try one thing. Okay, maybe try not to lose it. Yeah. So setting up a CI pipeline is not the easiest thing to do because now you have to deal with debugging things on a server that you don't necessarily control. And on top of that, there is this additional layer of complexity that you have to configure different services using some kind of config that your CI provider requires you to use. But usually with some kind of templates that we found on the internet, we can glue together some reasonable setup. That might work great when you start your project, but as the complexity of your code base grows, also the complexity of your CI starts growing. You start adding more and more tasks, you start building different versions of your release packages, you have more and more tests, and it starts to get frustrating to wait for your CI run to finish before you can merge your code, or maybe to wait for half an hour only to see that the pipeline has failed in some later stage because you made some silly mistake like unused variable, and that made your linter unhappy. So in this talk, I want to take a look at a few ideas to consider when it's time to improve your existing continuous integration. So first, we'll have a look at some improvement to our Docker setup. Then we will look at running things faster, for example, by configuring jobs so they don't have to wait for other unrelated stuff. Then I will have a look at not running unnecessary tasks or stopping them earlier. And finally, if I have some time left, I will share some miscellaneous tips and tricks. If we want to discuss continuous integration, we have to choose some platform because different services like GitLab, GitHub, CircleCI, and whatnot, they all require you to configure CI in a different way. I mean, the general idea stays the same. You write some kind of a config, but the way you write this config file differs between CI providers. So unfortunately, it's not possible to take your GitHub config, move it to GitLab, and expect it to work out of the box. So for the purpose of this talk, I chose GitLab. And that's mostly because most of my recent projects are using GitLab. But also, according to this Reddit survey, this is still the most popular option. But I am in no way related with GitLab. I know that they have paid plans, but everything I will be talking about can be found in the free version. And I personally never used GitLab. My clients did. We also need to have some code that our CI will actually run on. So I created a simple project that you can find under this link. It's a Django project with a very simple to-do app. If you don't know Django, don't worry, you don't have to know it. I use Django for the simple reason that a simple Django app by default is slightly bit more complex than a bare-bone Flask or Fast API. Out of the box, we'll have some migrations that we have to apply, and we will have generally a bit more files lying around, so it feels a bit more real world. So this example project has a to-do app that interacts with a database. It has a bunch of requirements. So this is mostly to slow down the build process. And it also has some tests that are slow because they either sleep or perform some needlessly large mathematical operation. Again, this is to slow down tests, so we have some room for improvement. And the build process uses Docker and Docker Compose. Docker Compose will set up two services, a Postgres database and a web container. And the web image is built from a pretty standard Docker file. So we specify Python 3.10 base image, we run pip, and then we start the server. I'm kind of scared to use the pointer here, so it works. I'm not going to touch it. Yeah, so this initial setup has a pipeline that takes around 6 minutes to finish. It runs 3 jobs. So we have a build that builds a Docker image. Then we have a test job that runs some migrations, and then it runs test. This stage is actually badly designed because the first Docker Compose will actually build the Docker image from scratch. I will address this issue in a moment. And then finally, we have a deploy stage that only prints a message to the screen. But if you look here, you can already see that it takes 54 seconds. So those 54 seconds is the time it takes for GitLab to provision a new container for a job. So keep that number in mind. And of course, this is an example project that is simple for the demonstration purpose. It's absolutely not production ready. So maybe try not to copy it and use it in production. So I mentioned that my example is using Docker. Docker or containers in general are now a common tool in the DevOps world. They are also very well supported by most of the CI providers. So if you're planning to deploy your application to some cloud provider, using Docker inside of your CI is a good idea. But even if you do development without Docker, it's rather easy to wrap your application in simple containers. So if you do use Docker, the first step to improve your CI is to actually take a look at your Docker file and make sure you don't have some obvious problems. So make sure that you are using layers caching during your build time correctly. Make sure you use tags so you know which image you use in your builds. Speaking of images, which one of those two you think is better? Slimbuster, which is a Debian-based image, or Alpine, which is a pretty bare-bone small Linux image? Slim. OK, so we have someone saying Slim. So if you use a Slimbuster, then you will have a larger image because you will have a lot of additional software that you don't necessarily need. So anyone here said Alpine? There are some people nodding heads. Yeah, but with Alpine, you actually have to install some additional tools even to be able to run pip. So there is no good answer here. If you use Alpine, it means that you will have to probably install some additional Linux libraries yourself. This will make your Docker file slightly more complex, and the build process might be longer, but the final image will be smaller, so it will be much faster to download it or push it back to the registry. On the other hand, Slimbuster is twice the size of Alpine, which is still not that bad, because if we use Buster, that's like 15 times the size of Alpine. So it will take longer to download. But chances are it will come with all the dependencies you need. So then you can just run pip install and you're ready to go. So in the end, the choice should depend on whether your pipelines spend more time building the images or pushing and pulling those images in your jobs. But Slimbuster is usually a good choice here. So one way we can also speed up our build time is to not build the Docker image in each job, but to actually build it once, push it to the container registry, and pull it in the consecutive jobs. So here we can see that even though we are building the Docker image in the build stage, when we run Docker Compose, it will also build the Docker image because jobs are independent. So the test job doesn't know that the image was built in the build job. We can fix that by pushing the container registry at the end of our build job and then pulling it at the beginning of the test job. And if we check this pull push Docker image branch in my example project, we can see that now the build time takes a bit longer, but the test job takes less time. But of course, the differences here are tiny. Like those few seconds might come from the fact that it took a bit longer to provision the runner for our job. And actually, if we check the test job in my example project, you can see that building a Docker image takes almost the same amount of time as pulling the Docker image from the registry. But again, your mileage may vary. If your build process takes long and you have many jobs, then it makes sense to pull this image at the beginning of each job from the registry. But if your build process is simple and fast, then maybe it will actually be faster to just build the Docker image from scratch. So another thing you can do if you end up building massive Docker images is to use a multi-stage build. Multi-stage build means that you will be using a separate image for the build process. So you copy a bunch of files, you install plenty of dependencies for the build process, then you run the build process that might create some temporary files and some cache files and so on. And that image can grow in size, but you don't really care because at the end, you will just take the results of your build process and move them to a new image without all this cache, without all those additional dependencies. You mean the screen? Okay. Yeah, you can do this now. I don't need this. You saw the slide. Yeah, so the multi-stage works very nice in languages where the build step requires you to install additional Linux dependencies, but the result of the build is a single binary, for example, in Rust. In the Python world, it doesn't matter that much. Will it? Okay, let's give it a moment. So in the Python world, it doesn't matter that much. Like in my example, I'm not even installing any Linux packages in our Slim Master. If I was using Alpine Linux and I was installing some additional Linux packages, then it might make difference, but in my case, it doesn't really matter. Let me get the slides back. They always move to the other side. All right. So let's leave Docker for now, and let's talk about CI pipelines. How can we make them run faster? So as your pipeline starts to grow bigger and bigger, and your stages start to include more jobs, you realize that maybe some jobs are unnecessarily waiting for their turn just because you assign them to some later stages. And in case you're curious what we are looking at, this is the pipeline of GitLab itself. So it's a pretty chunky boy. So you might want to look at the structure of your CI configuration and move things around. For example, instead of running your jobs in separate stages like here, we can run multiple jobs in one stage in parallel. So this pipeline will ultimately finish faster, except that what happens in one of the jobs fails. Now we are wasting computing resources running other jobs in this stage, even though we don't really care about the results of the static analysis or preparing the release, because we have to go and fix tests anyway. And there is actually an open issue about being able to cancel pending jobs if one of them fails, but it's open since 2018, so I would not get my hopes high that it's going to implement it any soon. So there are always some design considerations involved how you set up your pipelines, but in general, I would say that the time wasted waiting for the pipeline to finish, it's much more precious than a few dollars that you spend for the build minutes. So parallelizing things in general is a good idea. And there are two different ways how we can move things between stages. One way is called directed acyclic graph, or DAG, and you might know this concept from other tools. So with DAG, you can configure one job to start after another job, regardless of what stage they are in. For example, let's say you're testing your Python package under different Python versions, and for some reason you don't want to use a tool like Tox that can create multiple virtual environments with different Python versions. Instead, you decide to build different Python Docker images, and then run tests in those images, and then run releases. So here we have a, thank you. Here we have a build stage that has to finish before the test stage can start, and then we have the release stage. In the ideal world, all the builds will run in parallel and finish in more or less the same amount of time. In the real world, they won't. Like, some builds will take longer to finish, and for example, if you're using custom runners, that's okay. And for example, if you're using custom runners, then do I even see that? Okay, let's give it a moment. If you're using custom runners, then maybe your jobs have to wait in the queue before they can even start. And in the case of this slide that we no longer see, what's the point of the test for Python 3.8 to wait for build of Python 3. Oh, come on. Up. It's that. Oh, yeah. Now I can see my slides. Can you like gather here? Okay, can I like not mirror this guy? Okay. You know, they say a good speaker can give a talk without the slides. I'm really not a good speaker. I need those slides back. There's always this tension when it goes black. Is it going to show me my desktop or the blue screen again? Yay! No problem. Oh! Nope. There should be like those drums. Yes! Come on, come on, come on. It's not. Yes! Okay, quickly, quickly. All right, yeah. So that's where we can use DAG. So we can connect some jobs between the dependent. You saw the slide, just memorize it. So you can combine some jobs with their dependencies regardless of where they are in. So once the build job is done, then the test job can start, and then the release job can continue. And in terms of code, that's all we need. You saw it for a brief moment. There was this needs keyword where you have to specify which job has to finish before the next one can start. Well, I can drink water, actually. I never had so much time to drink water during my presentation. Well, you have to rely on your imagination. So DAGs are cool, but there is another way how you can connect jobs. So if you connect too many jobs using DAG, then that can be confusing. Oh, different colors. That's not intended. But OK, I don't mind the colors. You can also create a downstream pipeline. So you can like create mini pipelines that will be triggered from your parent pipelines. Let's say you're working on a project that is using a separate tech stack for a backend and for the front end. Let's say it's a Django REST framework with React on the front end. So then you have your backend code in the backend folder and your front end code in the front end folder. And your backend tests probably don't depend on having your front end up and running. And then also there is no point in having in running your backend test if you only change something in the front end. Yeah. I'm wondering how long is it going to last. We're going for a high score here. Yeah, so in this case, we can create a separate pipeline for the backend and separate for the front end. And in terms of the code, this is how we can implement it. So here we have two jobs, front end and backend. And then in the trigger, we say that the front end configuration is in this front end /GitLab CI, backend is in the backend /GitLab CI. And then we have a strategy. So in the strategy, we say that the parent pipeline depends on the result of the child pipeline. So if the child fails, the parent also should fail. If we don't specify the strategy, the parent pipeline will continue running other jobs even if this child pipeline fails. And then finally, under the under the rules, we can see that we should only run this pipeline when something changed in the front-end folder or something in the backend folder. So we don't run the pipeline if only something has changed. We don't run the backend pipeline if only the front-end has changed. So what else can we parallelize? We can parallelize tests. And most of you who already use PyTest, you probably know that there is this plugin called PyTest XDist that you can run PyTest on multiple CPU cores. And this is great if you have multiple CPU cores. But if you don't, you can run your test across multiple runners. This is especially useful when you want to dynamically spawn new runners. So you don't have like one huge, expensive multi-CPU server up and running all the time, but you spawn runners dynamically. And in terms of code, we have to install the PyTest test groups, and then we specify the parallel option, and we specify two options that you cannot see anymore, but you can connect them to GitLab variables, and then that will run your PyTest in separate jobs. So here we can see, here we cannot see that I have a separate branch where the slides will be available at the end, so you will be able to follow. So here we will have like 5 different jobs for tests, and as you can see, as you cannot see at the top, we got, with the build time, we got down from 6 minutes to 5 minutes, but in terms of cost, we basically doubled the cost because instead of running 3 job containers, we have 5 job containers for 5 different tests, and just starting a job container takes around 1 minute. So it will be faster, but it will be more expensive. One thing that we can also do, imagine things. You can also interrupt the job. So if you have a job running and you push some new code to a branch, then it no longer makes sense to run that job. So you can make your pipelines interruptible. And there are actually 2 parts to it. So in the settings, you can enable this auto-cancel redundant pipelines. And this will allow you to cancel the pipelines, but only when the currently running job is finished. So you can also, maybe you will see, you can also add a key to your configuration called interruptible true. And this will allow you to stop the job as soon as there is some new code. So if you have like a build job or a test job that's running, you can interrupt it in the middle of the run. You don't have to wait until the end of this job. But for example, if you have a deploy job, then you don't want to make it interruptible because you don't want to end up with like partially deployed code to your web server. You probably want to run this job and start another job as soon as possible. And another thing is to stop tasks in your job when it doesn't make sense to run it anymore. For example, if you require that your tests are passing in the merge request before the code gets merged, then what's the point of running the whole test suite in the master branch? You can stop after the first failure with the PyTest -x, because that's enough to tell you that, hey, there is something wrong with your master branch, and someone will have to run those tests locally anyway to fix them. So the job can start, and job can stop, and you can start another job. Yeah. So how else we can we can make our CI pipelines faster? Well, by not running things in the CI. So one of my biggest revelations was that not every check has to be done in every pipeline. For example, if you have a bunch of slow integration tests, you can run them only on your main branches. In my current project, the whole test suite takes around 40 minutes to run. So we just marked some of the tests as slow. And now we run only some of the tests on the merge request pipelines, and they take around 5 minutes to run. And then we run this whole slow test suite on the staging and master branches. So the merge request pipelines are faster, and we still get the results of the whole test run eventually on the master branch. And if you have like particularly slow jobs, you can run them manually or you can run them nightly. Yeah. So we got to the part with the random tips and tricks. Do we even have some time? Should I continue? All right. Yeah. So one random tip and tricks is about caching. So you can define some cache in your pipelines that specifies, for example, that pip can cache their files, and then installing pip packages will be a bit faster. But you can also specify cache policy. So by default, when you cache something in GitLab, at the beginning of the job, you pull the cache, you run the job, you push the cache. But for example, if your job is doing something destructive, you can disable pushing this cache back. So your job will just pull the cache, do whatever it wants, but it will not push things back. And with that, you can also select something called fast zip compression method, which allows you to select the compression level for your job. So you can select like the fastest method that will run well, the fastest, but the cache size will be a bit larger. So, yep.
Maybe if you switch down your, if you lower your resolution and
Yeah.
put it to 60 hertz.
I mean, I'm just almost done, so.
This resolution.
Yeah.
Oh, Jesus. I'm going to use less.
Sorry.
Now, how do I change resolution? No, that's arranged. So that's the thing with this guy. Mac doesn't. Yeah. No, it's not as easy as with. I mean, yeah, almost done. Well, should I wrap up or should I continue? Okay, I mean let's go to the conclusions anyway. So, the takeaway from this kind of failed talk is that learn concepts, not tools. So what I was showing you, well, showing you is a big word, was how to use GitLab CI. But I mean, whatever CI provider you use, there is a way to run tasks in parallel or sequentially. So once you know how that something can be done, it's just a matter of figuring out how to do it. I don't know why I'm still clicking the slides. There are no silver bullets in terms of a perfect CI. Like, should you use Alpine or should you use Debian Buster? Should you like build your Docker images in your job or should you pull them? The suspension is killing me. It really depends on your project. And not every check should be done in your every pipeline. Why this guy got stuck? I'm like, all right, yes. Not every check has to run in every pipeline, so just make your merge request pipelines fast and your main branches pipelines thorough. And if you think that you only set up your CI once at the beginning of your project and then you don't have to touch it again, think again. Outdated CI is also a technical debt, so it will make your code review slower, it will delay important feedback, and it will make developers more and more annoyed. So do yourself a favor, check from time to time what can be improved there. But in general, a well set up CI can be a great tool in your daily work. Thank you very much for listening and partially looking. Yeah, we can go with questions. Yeah, of course, we can go with questions.
We can. There are some questions. We can have 5 minutes more for questions if you want. What's a good way to debug building of Docker images? I've literally spent days to find tiny pesky mistakes in the past.
Oh, I did the same. I have no way. Like, I literally spent like 3 evenings trying to figure out what's going on in my CI because like I thought Docker containers could not talk to each other, and then I realized it's about the Postgres startup time, so you have to wait for the health check of the database, and just web was starting too fast before the database started, and I was like losing my mind there. So I have no way how to debug it. This is complex stuff. You needed someone who knows this stuff.
Which custom runner executor you recommend, Shell or Docker executor?
Honestly, I have no preference. I think in my examples, in the example repository, I think I used Shell, and at work we used Docker. But, well, depends. If you're using Docker already, then probably Docker.
Would it make sense to use modern workflow tools such as Apache Airflow for more complex CI setups?
Probably. Like the main benefit of like GitLab CI and other stuff is that it's built into where you store your code. So like for simple and like more advanced pipelines, it's fine. Like GitLab seems to be like quite advanced with what you can do there, but like if you need something very specific and you feel like Apache Workflow is a better choice, then yeah.
Do you run each test separately? It feels like that uses way more resources due to setup and destroy being done all the time.
If I run each test separately.
Do you run each test separately?
No, I just run PyTest and on everything.
Thank you very much. That was the question.
Thank you. No worries. That was fun.
talk about becoming a better Pythonista by abusing list comprehension and the walrus operator. Let's go, Nicola.
Hi, everybody. So today I do want to teach you a little bit about list comprehensions and comprehensions in general and the walrus operator. And I do think that the best way to learn something is, first of all, teach it to somebody else, which is what I'm doing. So it's all for me to actually make me learn about this. But it's also try to use these things in the worst possible ways. Because sooner or later, you'll always meet some kind of edge case which you didn't expect. And if you just abuse everything early on, you will hit all the edge cases and you will be able to actually use it from that point and on. So let's start immediately with the walrus operator. So if you don't know, but you should, the walrus operator allows you to set a variable value within an expression. And I do have here somewhere Carlo, which is of whose Pythonic skills are unmatched. However, when it was first introduced, I managed to find an example which totally confused it, because sometimes it's easy to understand incorrectly which is the order of executions of various expressions, and you just mess up the walrus operator entirely. So let's immediately jump into order of evaluations, because it's really important. And a couple of notes. First of all, that first thing allows you to, the first line is just print, but it actually prints a value just before actually having the function entirely. The second line is just true, but when it gets executed, it will print A. And this allows us to kind of understand which, what is being executed and what isn't. And the other couple of things you should know, like these are comprehensions. So first of all, first example, this is a list comprehension with, on the first lines, ternary operator, and then a function called write at the end, and each step has a print value. So the question is, what is going to be executed first and in what order? So which numbers are we actually going to see on the screen in what order? So I'm actually going to give you like 30 seconds to think about this, to read it. If this was a YouTube video, I would say stop the video and think it's 30 seconds just to see what's going on. And then you can raise your hand and try to give the solution. Somebody wants to try to give away the order of operations here? What am I going to see? What numbers am I going to see in what order? That's the question.
4, 5, 6, 1, 2, 1.
Exactly. 4, 5, 6, 2, 1. And why is that? So firstly, the outermost element is a list comprehension. So we want to know what we're actually iterating on, which is that print 4 inside of square brackets. Then we check the condition, which is the last thing. And we first do the function to be called, so print 5, and then we do the arguments, which is print 6. And then we go all the way back to the ternary operator. We do the condition first, which is the 2, and then since not print is true, we just get to the print 1, and the print 3 never actually gets executed. So this is the order. Why is it important to know this? Because these are some mistakes that I've seen around, which is exactly what we just saw, but using the walrus operator in the wrong order. In both cases, we get exception because num is not defined. And that is because we define it later than we actually use it. And visually, it seems correct because we first assign the value on the leftmost element, and then we use it on the right. But sometimes we execute parts of things on the right before the things on the left. So these are incorrect, and to fix them, you just have to move where you actually define num and so on. So what's the next slide, because I completely forgot? Okay, so let's now dive into a terrible idea, which I had whilst doing this presentation, and that is try to make this work. So we've got a function which is defined as an argument of itself. So I first define function which is print, and then I try to call it giving itself as an argument. Why would I do this? We don't care right now. Just let's try to do this. Does this work? Somebody can tell me whether this works or not, just if you type this line into Python.
I think it doesn't.
Why doesn't it?
Scopes, but I'm not sure about it.
It's not actually about scopes, which I originally thought I was going to talk about, but turns out not a big deal. There's something else which is bigger, which is the order of operation. We always first execute the function to be called, and then the arguments. So in this case, function, the leftmost one, is executed first, and it immediately raises an error because it's not defined, because it's an argument. But we can fix that. So we can use a kind of a trick, which we shouldn't use. There's no reason to, but we can make this work. So again, I'm going to give you 30 seconds to think this through, and then I'm sure there are many solutions, but just try to pick one. Ideas? Shall I give you a hint?
Parentheses, function was equal print, close, open, function. Close.
Okay. Yes, that would be defining the function directly as yes to be called. But I do actually want this to work. So I do want to define a function in the arguments and then be able to call it. So I'll give you a hint. So what could it be? This is just one solution. I'm sure there are many. Any ideas? Hands up. Nice. So this is my solution. I'm just going to wrap the first element inside of a lambda. So what this does is Python first asks, OK, do I have the function that I actually want to call? And in the previous case, it said, no, there isn't any. And that immediately gave an error. In this case, there's a lambda, and Python is just happy to know that there is a lambda. It's only when the function actually gets called, which is the last thing, that Python actually executes the things inside of the lambda, and in that case, function will be defined. So this works, and lambda in general are very, very useful to actually postpone when you want something to be executed, and if you have to bind something and then change the value, and you want a function to refer to the new value, you just put it inside of a lambda and execute it when you know that you have the correct value. So this is just one thing. And again, what's the next slide? Yes, of course, there's a big question here, which I'm totally ignoring, which is why would you care about all of this? And you shouldn't. But again, I do think that there are some corner cases that it might be good to know for the future. As an example, this is a function that is recursive, and it's also defined directly in one line. So I'm defining the usual function, and then I'm giving it a name, as you were saying previously, and then I'm passing it as an argument of the function itself. So in just one line, I'm able to do a recursive inline function. You shouldn't do this, ever, but you know. Still talking about how you can get the Walrus operator wrong. This is a question from Stack Overflow, and this is somebody complaining that the first two lines are the same. It's just changing the value it's comparing. The first one works, the second one doesn't. They look the same. And so this person rightfully says, this looks completely inconsistent. Again, he messed up the order of executions of things. So again, can you spot which is the mistake here? What's happening? Why does the second line not work? Yes?
Y is not yet defined.
Yes, that's what it says. And but why is it not? Why isn't it defined? Like, we do have a definition. Okay, come on. We do have a definition there of y, and the comparison fails, and thus. Yes. So basically, it does first the x part, which is 1. It checks whether 1 is strictly less than 1. It isn't. So it doesn't even bother to go on and actually define y. So it immediately raises an error. And now I've just slightly changed, yet again, to show how subtle these errors can be. Is this going to work? It's almost the same. I just changed one little detail. Is this going to work? I'm going to give you the answer. It does work, because same issue as before, except that now I do use the same variable on both lines, which means that on the second line, it's still defined from the first line. So it does work. It shouldn't. You might think that everything works if this works, but there's actually a big error there, because z is not going to actually get the correct value. Now, one last order. This is too boring. I don't have time for it. So switching to comprehensions, there are some good ones, the bad ones. The good ones is kind of what you would expect. These are comprehensions. I'm just assuming that you kind of know what they are. And they are almost perfectly consistent, except that the last one, if you use the tuple syntax, you would expect the value to be a tuple. It isn't. It's actually a generator. And I'm not going to get into what that means, but as a rough way to explain it, a very bad one. If you know iter, then generator is basically doing just list comprehension and then just throwing iter at it. Slight differences, but we don't really care about them. The main point is that the generators are lazy. And what that means is that when you actually write that code, and you run it, even if you have prints inside of it, nothing is actually going to get executed until you actually start iterating on the generator, which means that in a list comprehension, that one last line would print hi 10 times. This one doesn't. It doesn't do anything until you start iterating on it, which brings me to my proudest trick of this whole talk. Not yet. I just wanted to point this out. Again, I think you kind of know about this, but if you just throw a comprehension inside as an argument of a function call, it's the same thing as if you were just doing the generator and passing that as an argument, which means you can just use generators inside of sums as an example. It might help to clean the code. In general, if you have inside of an argument a list comprehension, most of the times you can just throw away the square brackets and it's still gonna work anyway. So that shouldn't be an issue. But yeah, it's a nice thing that you should probably know about. Now the trick. So this is quite a trick. So there's a line missing at the top that actually defines my list. So we don't know what my list is. The rest of it is pretty simple. I just set a variable, answer. I iterate over a list, or over my list, whilst doing absolutely nothing. And just by doing that, my value of answer has changed. How could that happen? And the most people most experienced with Python would think of like setting a custom iter method of a class, and then that one can try to modify the global variables. It's much simpler than that. So yet again, I'm going to give you a little bit of time to think this through and try to find a possible value for my list. That's very simple, like it's 27 character long, so very short, and yet it manages to mess up with my global variables, even if I'm not doing anything with it. What could it be?
A generator expression comparison with what other serial operator needs?
Yes. So it's just that. So I've got a generator, which is lazy, again, so it doesn't get immediately executed, which means that the variable is not going to be set until I actually start iterating on my list. And as soon as I do that, the global variables change. And this is kind of a big deal because I'm able to write something in a very simple way that behaves in a way that you would never expect. If you start iterating on a variable, anything, and you just not do anything with it, you wouldn't expect your global variables to change, but you can, in a very simple way. Don't ever do this, by the way. And if you do this, don't absolutely say, I told you about this. I didn't. But now we get to things that are not as tricky, but I still get them wrong. So this is nested comprehensions. So a comprehension is inside of a comprehension. And the thing is that you would expect that stuff like this basically behaves the same. Just to say it very quickly. Of course, the first one is going to get you a list of lists, whereas the second one is just going to give you one list. Thing is, when you do this, the order, again, is actually inverted. So in the second case, for value in row, for row in column, that's going to throw an exception because you first do for value in row, and then you do for row in column, and row is undefined. Whereas in the first line, which looks basically the same, that won't actually work because it first does for row in column, and then it goes back to for value in row. So as a general rule, nested comprehensions, right to left, not nested left to right, as you would normally expect. How much time do I have left? Time out?
40 seconds.
40 seconds. I don't know what to do with them. Yes, that was kind of everything, but if you feel like you want to spend the 30 seconds in a good way, you can try to figure out what's the value of this and what's the value of A as soon as this finished. It's not easy.
Okay, so a big wave for Nicolas. We have 5 minutes for questions. You can use a Slido just like we did with Samantha. So, while I open Slido, you can explain just this one?
Yes, so basically we start from the top, we go to the bottom. So A is 5, which is true, so we get to the line under it, which sets it to 0. Which is false, so we get to the line underneath, which raises by 1, so it's 1. And this is true, so it goes to the line after that, which gets to 2, which is still true, so I still get to the line under it. 2 minus 2 is 0, which is false, so it ends there, and you have that the value of the whole thing is 0, whereas A is still 2 because I don't set the new value.
Great, so We have from now on question. Why should we use list comprehension? Is it useful to improve the performance of code?
Oh, I guess I should have talked about that, I guess. Yeah, no.
Oh, we have 3 minutes.
We have 3 minutes. So, no, I'm not sure about the performance. I do think that it helps a lot to improve the readability of the code, being able to actually better understand what's going on. It really depends on the use case. So if you've got like nested comprehensions, then you probably want to avoid that and just go with normal loops. But if you just have one for loop that you could just replace in one line with a comprehension, it could be easier to read. This is all trying to make it harder than it seems, because if you want to use a lot of comprehensions, then it is also worth noticing that sometimes you're dealing with some weird programs that only accept expressions and not statements. So sometimes you do have to write just one line of code to do something. Maybe you're working with some modding of some games and it just accepts one command and it has to be an expression. In that case, you have to use expressions, you have to use comprehensions and such.
Great talk. Another question, but that's a great wave again for you. Great talk. I loved it. They say.
Thank you.
So, thank you, Nicola.
Ok, ottimo, da sapere.
I mean, we will see if you do it again after the talk.
Okay. So, load your Slido app. We just have to wait 1 minute. I'm not very good at telling jokes. So, I will prepare myself more next time.
By the way, if somebody wants to sit down on a chair, there are a couple there.
Yes, please. And
I mean, I know the floor is pretty comfortable here, but
yeah, but we cannot pack that much the room.
yeah.
So, is this your first Python conference?
Yeah, it's the first PyCon conference.
At all, for as a speaker or as even as an attendee?
Yeah, absolutely. It's my first time ever here. Last year we sent 2 people from my company. This year we are 6, and let's see how the progression goes.
Yeah. Usually it's a Fibonacci series.
I hope so, because it would spell good for the company.
So we will have a Q&A. So how many have prepared the Slido app? The Slido app? I don't know the exact pronunciation. How many Slido users here? Okay, 2. Okay, if you have some questions and you don't have Slido, you can ask. Okay, welcome to the Hitchhiker's Guide to Async.io by... Excuse me? No, the Slido, okay. So welcome to the Hitchhiker's Guide to Async.io by Emanuele Fabiani. And well, let's start.
Very good. I mean, 2 rounds of applause before even starting to speak, that's a little bit of pressure. Okay. Thank you. Let's get on with it. So we all know that the Python standard library is pretty stable and we'll like it. However, in the last 3 years, there were 2 packages that got massive evolution. The first one is typing, of course, and the second one, you guessed it. Async.io is the Python implementation of asynchronous programming. It's a fairly new concept in the Python ecosystem. The first stable implementation of Async.io was introduced in the standard library in Python 3.5. That's 2015, so more or less 8 years ago. However, in 8 years, Async.io has become the backbone of all the most popular frameworks out there. FastAPI, Django, you name it, they're all based on asynchronous programming. Asynchronous programming is a set of primitives to fake parallelism, getting the advantages of parallelism without using multiple threads or multiple cores. That is, all of the fun without edges. That would be great, but there is also the other side of the medal, of course. I think that the core of Async.io and asynchronous programming overall can be summed up with waiting smart. It's nothing more than a smart way of handling waiting time. Why is waiting time a big deal with modern hardware? Well, let's play a game. Let's say that one CPU cycle does not last fraction of a nanosecond as it does in the reality, but it lasts 1 second just to get closer to the human timescale. Then if a CPU cycle lasts 1 second, fetching some data from the L1 cache, the fastest memory out there, takes 3 seconds, 3 CPU cycles. going to the random access memory, the main memory of the system, it's in the order of minutes, 4 minutes, let's say. Fetching some data from the network that is completing a request-response HTTP cycle is 7.6 years. So we are talking seconds against years. It's like the time you spend asking something from the Italian public administration and getting the answer back. It's the same time scale. So the point is, you do not want to wait years for something that can last just seconds. Very good. In the next 20 minutes, I will try, 17. I will try to first introduce you to some basic ideas: concurrency, parallelism, threading, processing, multiprocessing, sorry, and asynchronous programming. With that out of the way, I will try to show you some basic examples to see how async I/O works. And then we will try to go a little bit deeper, untangling the processes below async I/O, trying to see how it really works on a lower level. We will conclude by discussing a little bit when to use async I/O, how to use it, what are the main pitfalls of this style of programming. But any hitchhikers, should start somewhere. What better place with a lot of movement, lots of cars, than, oops, my bad. Good. Than a McDonald's. You see, a McDonald's works a little bit like this. You go there is just one waiter. You give your order. The waiter passes the order to the kitchen and then serves the next customer taking the order, the next customer taking the order. When a meal is ready, the waiter gets the meal from the kitchen and he delivers it to the customer that has requested it. That's a smart way of waiting, because it's not waiting at all. He's just performing the fast operation, handing over the task to another actor, which is way slower than him. I'm just using the male adjective, but I mean, I don't think that anyone gets offended for the McDonald's. And then, when the result is ready, he takes over again. So it's a way of avoiding to wait without parallelizing the work. Compare that to a post office. If you go to a post office, you have plenty of clerks waiting for customers to serve. Once you go to a clerk which is free, then the clerk is yours. If you have to fill a form, you stay there, basically wasting the clerk's time, and fill a form in front of him. Then, when you're done, you hand over the form, and the clerk can serve another customer. That's real parallelism. You have multiple resources doing the job. In the McDonald's, you don't. You see the difference? Okay, let's get out of the metaphor, and let's go to real computer science terminology. In Python, you have 3 ways of achieving or faking parallelism. Let's discuss immediately about the about the only way of achieving real parallelism in Python, and that's using multiprocessing. Multiprocessing spawns different processes, each of them with its own interpreter. So it's basically different copies, different Python interpreters that run in parallel on different CPU cores. Is it good? Is it bad? Well, it's great. It's real parallelism. You're using multiple computational resources. However, that's very heavy. Spawning a process for each task that you're going to perform requires a lot of overhead. And multiprocess communication is difficult. So when do you want to use it? When you have computationally intensive tasks that really take advantage of having multiple computational resources allocated to them. You don't want to have 3, 6, 16 Python interpreters wasting the time of your course, staying idle and waiting for something external to happen. Very good. Second one is threading. threading means that you are creating multiple tasks that are assigned, each of them, to a specific thread. Threads are operating system objects. That is, they're executed on the different cores as the operating system wants. So the point is that you don't know when a task will be executing on the core. The operating system does the job. It can start the task, it can end the task, it can pause the task. You don't have control. Python has the infamous global interpreter lock. It means that the Python interpreter can run only on one core, one and only one. That means that you can have 1,000 threads, not a great idea, but you can have 1,000 threads, but they will run all on the same core, and they will be handled by the operating system. Async I/O implements a different paradigm. It implements cooperative multitasking. That is, you, the developer, have the control about when a task gets another round of applause, maybe?
Hai risettato a 50?
Sì.
Ok, vai continua, tranquillo.
It looks like we are having, should I go on? Okay, good. I mean, let's go. So I was saying that asynchronous programming has a different idea. It gives you, the developer, the ability to suspend and resume tasks. Again, it uses just one thread, just one core. But it's much more, it's much better for I/O-bound applications. That is, assume you want to call an HTTP API. It's very fast to perform the request, then you have to wait, and then it's also very fast to process the response. What you want is to free the computational resources while the network is performing the operation and you're waiting for the response to come. And that's exactly where async I/O comes handy. So now we are really in trouble because there is the live coding part and it's very hard to do without the monitor. So I'm not sure what I'm supposed to do.
Riverifichi per favore. Abbiamo messo 50. No, verifica se non... No, verifica per favore l'impostazione.
Potete portare il portatile lì vicino a dove c'è l'attacco al fornitore.
50. 50.
Quanto è la risoluzione?
50.
La risoluzione 1900.
La soluzione è quella del Mac standard. Ma non...
Ma è andato bene fino adesso.
Cioè
Se lo
1920
faccio-
per 1080, ma sappiamo, ci hanno detto. Questa è la risoluzione.
Advanced.
Non so.
Non so dire. Il problema è che crashano tutte e tre, capito? Cioè uno non
Va
si sa
bene,
quale.
allora vai avanti.
Vado a caso. Ok.
No, lascia il 50, sì, sì.
Okay, let's hope. No, now the computer is not working. I mean, I'm not sure what these settings did, but it crashed my Mac. And that's not easy.
Marto facciamo?
Sì. Okay, let's try. So this is the classic hello world with async IO. We need to note a few things here. First one is that we are not defining a main function. We are defining a main coroutine. You see async def. Coroutines are just like functions, but they have the ability that functions do not have to stop and resume the execution. They're more or less like generators. Actually, they are built on top of generators in Python, and that's their advantages, their advantage over normal functions. Inside a coroutine, and only inside a coroutine, you can use the await keyword. The await keyword is basically, look, now I'm going to perform an operation which may require a long wait. So just put a flag here, give the CPU away to someone else that must do some work, and then come back here, awaken me when the data that I need are available. So the other thing that we must note is that we're not calling the main function as we would in a normal synchronous code, but we are running async.io.run. Async.io.run is the top level executor for asynchronous code. If you enter async.io.run and you inspect the code, you would see something like this. Well, a well-engineered version of this. What we are doing is using a very important object that is the Python event loop to run the asynchronous code. The event loop is the only object in Python that is allowed, that is capable of running asynchronous code. That is, it's the only object that can understand async and await. I need to skip something. I will skip this one. So let's see something useful. Let's try to use concurrency to speed up this kind of operation. So here we are just mocking some long-lasting operation, send crow. Let's say I'm a fan of Game of Thrones, that's why I send crow. But apart of that, the idea is that send crowd is maybe a call to an HTTP service that returns the response after 1 second. Note that I'm not using the usual sleep function of Python, but I'm using the asynchronous async.io.sleep. We will see how it works in a moment. Then I'm using async.io.gather for the free to run the free asynchronous operations. The idea is that if this code was executed synchronously, it would send the first crow, wait 1 second, get the crow back. Then send the second crow, wait 1 second, get the crow back, and so on. So total elapsed time, 3 seconds. Let's say 3.001 for the sake of the argument. And out of the 3.001 seconds of elapsed time, then exactly 3 seconds are wasted because the CPU is sitting there doing nothing. What we want to do is to send the first crow, send the second one, send the third one, and then wait for the first one to come back, the second one to come back, and the third one to come back. That's smarter. That's the McDonald's waiter. And that's exactly what happens here. If I run the right script, that is. Right? So total elapsed time, 1.001 second. That is 1 second wasted waiting and 0.001 used in performing operation on the CPU. Okay, so we understand that async.io.gather makes some magic. We understand that this async await stuff should do something, but what is it doing? Okay, I'm not making the mistake of putting this full screen again. Let's go with this. What is happening is this thing here. That's very important to understand how async.io works. That's how async.io works. God.
Però mettere 59 di frequenza.
Già 50.
Prova, c'è 59? Prova
No, non
60
c'è.
allora.
Non posso più fare niente.
Scusami.
Ok, facciamo quello di
59 e
default.
94, guarda che c'è.
Facciamo questo?
Vai.
Ok. So that's the important. I mean, come on. I would go just like that. That's the important slide. What happens is you run in a single thread. You run in the event loop. When in an asynchronous function you call await, what happens is I'm trying to handling some input-output operation. That is, I'm trying to reading or writing into some socket. I mean the operating system socket, not the network socket, right? So I'm going to perform both the operations. So let's say that I want to call an HTTP service. I'm trying to do the request, and that's fast. But then I'm also trying to read from the socket that should contain the response. And that's not going to happen because the response is not there. But I try to do anyway immediately. Okay? So when the event loop understands that the code is trying to perform an operation from a socket that is not ready, what it does is taking note of the coroutine that is trying to perform the operation and the socket that it is trying to read or write. Just takes notes, okay? Then it leaves the coroutine there, interrupts the execution, that's the await, and goes to the task queue. So it tries to look for another coroutine that is ready to be executed. It finds one. That's the second send crawl. The story repeats. It goes to the point where the coroutine gets interrupted, and it takes note. Now you have a mapping with two coroutines assigned to two different sockets, right? You get a third one. And then you run out of task to run. What the event loop does there is to call the select system call. The select system call, basically, it's a blocking call. So now the CPU is really idle, waiting for something. But what it's waiting for is a signal from the operating system. So it has handed over the control to the operating system. And the operating system is going to wake up the event loop when either of the freeze and crawl completes. So when one of the three sockets that we are trying to read if we were calling a web service is available, then the event loop gets woken up by the operating system. And then it resumes the execution of the code sequentially from the await, right? Then again, it completes the task. It tries to find another task to execute. Is it there? No. Call the select system call and hand over the control to the operating system. The operating system will wake you up, and again and again and again. Okay? You see the magic. There is no stochastic behavior there. The code is always executed sequentially. The only thing for which you're handing over the control to the operating system is to wake you up when the data is available. So you're not, you don't have to handle thread communication. You don't have to handle all these weird errors and bugs that come up with threading and so on. It's much simpler. It's all about waiting in a smart way. However, if you make the mistake of scheduling in the event loop a long-lasting coroutine, that is a coroutine which is not I/O bound, which has not to wait up until some data becomes available, but is maybe, I don't know, performing a mathematical optimization, so a very CPU-heavy task, that coroutine will never get suspended. So the task will keep populating the task queue, and your application will basically be stuck. That's why in FastAPI you should use background tasks for long-lasting operations and don't do it in asynchronous coroutines that implement the APIs. Very good.
Can I ask a short question? Can you give it back?
Sorry?
Can you give it back to the event pool for long-lasting tasks?
No. No, you can't.
Slido, please.
Okay. So what I would like to do in the last 2 minutes that I have is to try and show you a real example where async I/O is useful. So what we want to do here is to perform multiple HTTP requests using concurrency. So we want that at any given time, just 3 requests are on the network. Why? Because we don't want to perform a denial of service attack against HTTP bin. So we use a semaphore. A semaphore is a primitive, like a threading semaphore, it's the same thing, that limits the amounts of concurrent code that can execute at the same time. What we are doing here is creating 20 tasks, right? Tasks are just wrappers of coroutines, so are objects that can be awaited. We are not awaiting anything because from Python 3.11, the task group automatically awaits all the tasks that you create with the task group itself when the context manager gets into the asynchronous exit method. So at line 22, let's say, we will await all the 20 tasks. But remember, we have a semaphore with maximum concurrency 3, so only 3 coroutines will be executed by the event loop at any given time. Then what we will do is just wait for everything to complete, and that's done by the asynchronous exit method of the task group at line 22. We will check the exception, we will check the cancellation, and then we will print the results. They are just sequential integers. So that's a very complex way of computing a sum of the first 20 natural numbers. I don't have the heart of running this, but I will tell you that it's on GitHub and it works. Trust me, I'm an engineer. With that being said, questions, please.
Thank you, Emanuele. Thank you, Emanuele. Well, there is one question. For now, I will just read it. How should Python solve the sync/async function caller problem in a future language version? I don't know exactly what function caller mean, but if there is people who ask the question, maybe you can clarify a bit.
I mean, I would say that the problem of distinguishing synchronous code and asynchronous code is already solved. Asynchronous code is implemented by the coroutines that you define with async def, and it's the only, they're the only piece of code that can have a wait inside them. So that's the distinction.
Okay, so I think we can have 1 minute more if you want to, if anybody's okay.
Are there many different event executors? Like, I think there are different ways of managing the queue, if you can tell some differences.
Yes, there are. So first, Python has 2 default implementations of the event loop. One that is working only on Windows and one that is working on every operating system, and the second one is the one you get by default when you use async.io.run. But you can write your own event loop if you really want. You can write your own event loop, but I would not do that. For the executors, let's say that the most interesting stuff that you can do is to use the thread pool executor. That is not asynchronous programming, but it is threading. So under the hood, even though it is made available also in the async.io library, what it does is actually creating threads to run your code. That's usually what you do when you want to run long-lasting computations, because threads are preemptive and are managed by the operating system. So if a thread gets the control of the CPU and wants to run longer, the operating system just says no.
Okay, thank you, Emanuele. I'm very sorry for all the e fra 56 secondi il nostro Alessandro Molina, che viene da Cuneo.
Da Torino. Lo sai meglio di me.
Vabbè, io volevo fare la squallida battuta di Alessandro Molina che viene all'ombra della mole, però diciamo, so che in questi 32 secondi non stanno registrando. Spada, esatto.
Cabaret.
E fra poco sarò serissimo. Funziona, sì, perché...
Forse.
Mi raccomando, no full screen.
È già in full screen.
No, no code examples, non eseguire nulla.
Non toccare niente. Lasciamo questa slide tutto.
Disattiva per favore quel sospendi, no? Ogni tanto poi se sospendi quello si chiude.
Cerco di...
E adesso ciao a tutti, presentiamo qua il fantastico Alessandro Molina che dal 1915 presenta ad ogni conferenza Python, che ci parlerà di Apache Arrow, anzi Apache Arrow as a full stack data engineering solution, ma in italiano. Un grande applauso per Alex Molina. Apache Arrow!
Allora, spero che le slide in inglese non siano un problema, perché alcune di esse le avevo già pronte, quindi ho modificato, ho usato tenere tutto in inglese. Ok, iniziamo a parlare un pochino di Apache Arrow. Non so quanta gente lo abbia già sentito, lo abbia usato o sia a conoscenza di che cos'è in generale. Diciamo che è tantissime cose. Nasce come al suo cuore un formato dati per rappresentare i dati in memoria e rappresentare i dati su disco in alcuni casi, e scambiare dati via rete o insomma in generale per trasferire e far collaborare librerie diverse che implementano questo formato. Ovviamente però nel momento in cui tu hai un formato dati hai bisogno di avere una, diciamo, implementazione standard di questo formato dati, per cui nel tempo Arrow si è evoluto dall'essere un formato dati ad avere la sua implementazione in questo formato, iniziava ad avere un formato per lo storage su disco, per la trasmissione in rete, una libreria che permettesse di caricare i dati nei formati più standard come CSV, Parquet o quello che volete e convertirli nel formato Arrow. Poi pian piano si è aggiunto un engine per la computazione su questi dati che erano nel formato in memorico, il supporto per dati tabellari, ultimamente un sistema di query engine e un sistema di gestione dei dataset partizionati. Quindi oggigiorno Arrow è in verità una grossissima framework che include al suo interno casi d'uso molto diversi. Posso capire che le persone che lo approcciano per la prima volta, quando guardano la documentazione, non capiscono nemmeno bene per cosa gli può essere utile, perché fa talmente tante cose che può diventare un po' confusionario. Diciamo che come Pythonisti il nostro entry point ad Arrow è PyArrow, che è l'implementazione per Python, e sarà quello che probabilmente vi troverete a usare sempre. Alcune librerie Python si appoggiano all'implementazione C++ di Arrow per velocizzare l'esecuzione al loro interno, però come Pythonisti noi approcceremo quasi sempre PyArrow o l'eventuale libreria Python che ci interfaccia a esso. Un'altra delle ragioni per cui Arrow è diventato importante è che il formato dati era molto efficace ed era efficiente e quindi si è iniziato a pensare che potesse diventare un canale di comunicazione tra librerie e framework diversi. Quindi diciamo che invece di dover copiare i dati da Pandas a, che ne so, Spark o qualsiasi altra cosa vi venga in mente e convertirli dalla rappresentazione che aveva in memoria Pandas o NumPy a quella che aveva ad esempio Spark, che era un processo costoso, nel momento in cui tutti quanti avessero abbracciato Apache Arrow come formato di dati, queste librerie avrebbero potuto iniziare a scambiarsi i dati senza nessun costo. Addirittura nella maggior parte dei casi ci sono alcuni tipi che nell'implementazione di Arrow sono un po' più complessi, ma per la maggior parte dei tipi base, come possono essere interi, float o tipi simili, la traduzione da quei dati che avete in PyArrow ad esempio NumPy o Pandas è praticamente istantanea, nel senso che non deve avvenire quasi nessuna conversione per la maggior parte di questi tipi, perché condividono entrambi il supporto nativo per il formato dati in cui Arrow li archivia, diciamo. E in alcuni rari casi c'è bisogno di effettuare una vera e propria conversione, perché per esempio adesso andiamo a vedere gli array in Arrow, che sono, diciamo, la base di tutto ciò che poi è Arrow. Siccome Arrow comunque è nato per gestire dati in forma colonnare, che è il caso d'uso più frequente nell'ambito dell'analisi dei dati. Quindi il suo fondamento è una colonna di dati e quindi, diciamo, un array. A questo livello, quando voi operate con un array di Arrow, praticamente è come se stesse usando un NumPy, cioè l'esperienza utente non è così dissimile, né le cose che ci puoi fare sono così diverse. Però ci sono alcune differenze tipiche tra l'implementazione di NumPy e l'implementazione di PyArrow che fanno sì che PyArrow sia leggermente migliore come formato dati. Per esempio, non so se voi avete presente, in NumPy la gestione dei dati nulli, del missing data, non è proprio una delle cose più pensate sin dall'origine della libreria, diciamo, è un po' aggiunta a posteriori. Invece in Arrow l'implementazione dei missing data è qualcosa che è nativa nel formato stesso, per cui un array numerico tipicamente ha i dati in sé e un secondo array di bit in cui viene segnalato se è missing o no. In alcuni casi questo può essere molto utile perché in certi contesti un dato può essere mancante per ragioni diverse, quindi io posso marcarlo come mancante, ma comunque poter voler avere un valore di quel dato, perché se io sto facendo un sondaggio può essere mancante perché tu non hai risposto alla domanda, o mancante perché hai scritto che non vuoi condividere quell'informazione, o esempi del genere. Okay? Inoltre l'implementazione delle stringhe è gestita molto meglio, perché se voi lo sapete in NumPy le stringhe sono fondamentalmente quelle Python e il supporto per esse quindi non è ottimizzato in nessun modo particolare, avete comunque a che fare con puntatori a oggetti Python che poi manipolate come manipolereste qualsiasi altro oggetto Python. In Arrow invece il supporto per le stringhe è nativo ed è garantito che siano implementate come un unico buffer continuo, quindi non è che ogni stringa ha il suo buffer di memoria, c'è un solo buffer per l'intero array all'interno di cui compaiono tutte le stringhe. E voi potreste dire, vabbè, ma a me come utente che me frega. È utile perché se voi volete applicare operazioni sull'intera colonna, questo vi permette di usare implementazioni vettorizzate di quelle operazioni, quindi avere una maggiore velocità di esecuzione rispetto ad avere 200 aree di memoria separate a cui punta il vostro array, diciamo. Ovviamente, siccome nell'analisi dei dati io raramente lavoro con una sola colonna, di solito lavoro con un'aggregazione di colonne, quindi ho bisogno di qualcosa che mi rappresenti questo insieme di colonne. In PyArrow questo oggetto è la table, okay? Molto banalmente. Le table però non sono basate puramente sugli array, sono basate su un concetto che sono i chunked array, che vuol dire che sono array che sono fatti da altri piccoli array al loro interno. Perché? Beh, in molti casi in verità il vostro chunked array sarà fatto da un solo array all'interno, ma nel caso in cui voi vogliate aggiungere delle righe, usare questa implementazione è molto più efficiente perché non devo riallocare l'intera colonna per aggiungere delle righe. Posso solo appenderla al chunked array e basta. Diciamo che qua potete, se prima potevamo pensare agli array come l'equivalente in NumPy, possiamo pensare alle table un po' come i data frame di Pandas. In verità questa è un'eresia perché i data frame di Pandas fanno miliardi di cose in più. Allora ricordatevi sempre che il suo principale scopo è rappresentare i dati e poi dopo ci si aspetta che ci siano altre librerie a implementare eventuali operazioni su quei dati. Quindi ora abbiamo capito che le tabelle in Arrow sono fatte a tante colonne e possiamo vedere un pochino come funzionano. Non è così diverso da come vi aspettereste. Una tabella è una collezione di array con dei nomi associati, in modo tale che sappiate come chiamare le colonne, e potete prendere tutte le righe che vi interessano a questa tabella, eseguire operazioni sulle singole colonne della tabella, avere informazioni sullo schema della tabella e così via. Esiste poi una componente di Arrow che è stata aggiunta diciamo da un annetto e che si chiama Asero, che è l'engine computazionale, che è in grado di eseguire operazioni complesse, pipeline complesse sulle tabelle e su anche altri formati di dati interni ad Arrow come il record batch o simili. Quindi usando Asero posso eseguire delle vere e proprie analisi dei dati. In questo caso vi ho messo un esempio in cui creo una tabella, vado a filtrarmelo per i campi in cui nella colonna values c'è 4, oppure vado a eseguire una group by per avere il conto di quanto fa la somma per ogni chiave, diciamo, oppure posso eseguire delle join tra tabelle diverse. Okay. Alcune operazioni, le più comuni, come appunto filtri, aggregazioni, join, sono esposte direttamente come metodi alla tabella per convenienza, ma in verità al loro interno vanno a creare una pipeline, un piano di esecuzione per Asero, glielo mando, gli chiedo di eseguirlo e quello dà indietro i dati. Quindi se voi volete, dall'ultima release di Arrow, dalla 12 è stato esposto proprio Asero come API direttamente usabile, potete costruire il piano totalmente custom che volete voi e dirgli eseguimelo. E tendenzialmente l'implementazione che abbiamo in Arrow è molto veloce, perché è tutto quanto, come vi dicevo prima, tendenzialmente implementato in CPV e con vettorizzazione. Quindi è abbastanza efficiente nel suo lavoro. Qui ad esempio vi ho messo un esempio di contare i valori unici all'interno di una colonna. Il modo più comune per farlo con NumPy è usare unique con ritornami i contatori, il numero di volte che compare un valore, e la stessa operazione se la faccio con Arrow e la funzione value counts è parecchie volte più veloce, come potete vedere. Non è detto che sia così per tutto, ci saranno sicuramente operazioni specifiche su cui sono equivalenti o cose del genere. Non tutti i kernel all'interno di Arrow rallentando troppo o funziona? No, questo è Sì? Funziona? Ok. Una cosa che ci ha insegnato a lavorare in informatica è di avere sempre un fallback per qualsiasi cosa che si rompeva di sicuro. Ok, questo talk, come avete visto all'inizio, è specificatamente su come Arrow può essere uno stack completo per lavorare con i dati. Quindi, ad esempio, vi voglio introdurre quella che è la filiera base di quello che può essere lavorare con Apache Arrow. Sicuramente abbiamo, come dicevamo prima, un'implementazione di storage dei dati che può essere nel formato nativo di Arrow, che è conveniente perché ci consente di fare memory mapping di quei dati direttamente, oppure in Parquet, oppure in Orc, oppure in altri CSV o altri dati, i quali poi vanno nel formato in memoria che può essere analizzato da Asero e può mandarci indietro i dati via rete usando Arrowflight, che è l'implementazione per la trasmissione dei dati sulla rete. Arrowflight è fondamentalmente un'evoluzione di gRPC, dove però la parte di encoding del messaggio gRPC è stata sostituita con una trasmissione diretta dei dati in formato Arrow. Quindi non avviene più nessun encoding, mando i dati come ce li avevo in memoria, li spedisco fondamentalmente alla rete. Perché questo è importante? Perché rispetto ad altri sistemi di comunicazione con database o altro, l'impatto sulle performance è evidente. Finché siamo su piccoli moli di dati non guadagniamo molto perché è più la latenza di setappare la connessione e altro che pesa. Ma quando iniziamo ad andare sui milioni o miliardi di record, cioè c'è una differenza abissale tra il tempo che ci va a trasmetterli con Flight rispetto a ODBC o equivalenti implementazioni per l'accesso ai dati. Quindi se usate Flight, i vostri dati voleranno sulla rete per davvero, in quanto è molto efficace. Nel tempo poi lo stack di Arrow si è evoluto, è diventato molto più complesso e oggigiorno fornisce anche componenti come Nano Arrow, che è una micro implementazione del formato dati di Arrow. Arrow è una libreria molto corposa, se l'unica cosa che a voi serve è capire i dati che vi arrivano già in formato Arrow, non avete bisogno dell'intero framework Arrow, vi basta tirarvi dentro Nano Arrow e usare solo quello, che alla fine Nano Arrow è stato volutamente implementato come una libreria che può essere vendorizzata nel vostro codice, quindi non c'è da installare componenti esterni, linkare, cioè prendete il file, lo copiate nella vostra directory e finito lì fondamentalmente. Poi abbiamo aggiunto, come dicevamo, il layer di rete con Flight, ma su questo sono stati costruiti canali di comunicazioni specifici per i database. Quindi abbiamo FlySQL, che è specifico per trasmettere query verso un database e ricevere i dati in formato Arrow. Abbiamo ADBC, che è la versione più agnostica, è un driver di connessione a qualsiasi database, sia che implementi FlySQL o no, non è importante, purché il database parli nativamente Arrow. Quindi abbiamo poi FlySQL, che è il nostro cuore di trasmissione, e varie librerie possono in teoria interfacciarsi con esso per trasmettere query e risultati di query. Ovviamente questo dà il vantaggio di avere una API standard con cui si può lavorare sui database e il beneficio di velocità di PyArrow. Ma vi ho parlato anche di ADBC, quindi qual è la differenza? Perché dovrei usare uno o l'altro? Fondamentalmente, se vedete questo grafico, sia ADBC che FlySQL sono Arrow native, cioè trasmettono dati nel formato Arrow. Ma FlySQL è una componente che va implementata dal database stesso. Okay? Quindi per poterlo usare il database deve avere a disposizione un endpoint FlySQL. E DBC invece è una libreria client che cerca di fornire connessione a quanti più database possibili trasmettendo i dati nel formato ARO. Quindi per esempio se voi vi serve connettervi a Postgres, FlySQL non lo fa perché Postgres non implementa FlySQL e IDBC vi consente di connettervi a Postgres. Perfetto. Poi abbiamo, uscendo da ARO, c'è anche tutto uno stack che è un ecosistema attorno ad esso. Solitamente una delle librerie più usate per interfacciarci con Compute Engine è IBIS, che fondamentalmente è un'implementazione di una libreria di data frame che però non ha al suo interno l'implementazione computazionale. Si interfaccia a database, a Compute Engine, a quello che a voi serve. IBIS è in grado di compilare le espressioni che voi create sia in SQL sia in Substrate o nel caso di Pandas in espressioni Pandas. E in questo caso mi concentro un po' di più su Substrate perché SQL è ovvio. Substrate invece è una libreria per rappresentare query plan generici che poi possono essere mandati a un qualsiasi Compute Engine che supporti ARO, Acero, DuckDB, Velox, e questi poi possono accedere ai dati dove li hanno. Quindi la prima cosa che vogliamo fare, se abbiamo tutto questo stack a disposizione, è ovviamente, deve essere facilissimo implementarmi il mio database da zero con tutto questo. E per certe definizioni di database questo può anche essere vero, perché questa è un'implementazione di, diciamo, una database da riga di comando in grado di eseguire query su file Parquet. Quindi gli passiamo la nostra query SQL, lui la converte, la compila in Substrate, la manda ad Acero come engine di esecuzione e me la dà indietro. L'unica cosa in cui usciamo da ARO è alla fine per stampare i risultati li ho convertiti in Pandas perché Pandas ha una rappresentazione delle tabelle che è un po' più carina da vedere nella shell, diciamo. Per tutto il resto ho usato solo unicamente ARO. E il risultato è questo. Io lancio il mio comando Python, gli passo la query, che in questo caso è dammi nome, cognome e lavoro di tutta la gente che vive in Canada, e lui mi dà indietro la tabella con tutti quei risultati. Tutto questo in 50 righe di codice per farvi capire quanti componenti avete già disponibili all'interno di ARO e del suo ecosistema per implementare una cosa del genere. Domande?
Beh, io direi siamo in anticipo di 2 minuti e 47 secondi.
Ho sbagliato ad alzare i cartelli. No, il time out ancora non l'ha alzato. Dovevo mettere una slide in più.
Ma no, abbiamo una carovana in realtà. Allora il mio che non le aggiorna.
Vai sulla tab live.
No, mi dice che non si riesce a connettere.
Sì. Fallback, ricordate prima il microfono.
Allora, quali sono i reali casi d'uso di ARO per lo sviluppatore finale? Salvo rari casi, non credo che sia necessario con oggetti a così basso livello.
È una interessante domanda. È vero, nella maggior parte dei casi voi probabilmente preferirete usare una libreria molto di più alto livello, come può essere Polars o recentemente Pandas ha iniziato a introdurre il supporto per ARO. PyARO è appunto una libreria più che interessa chi vuole implementare soluzioni per l'utente finale basate su ARO. Però vi ho fatto vedere prima che se ad esempio voi non volete installare uno stack di 27 componenti diversi, potreste benissimo usare solo unicamente PyARO, perché ad esempio una cosa che spesso in passato faceva la gente, adesso Pandas ha supporto nativo, se voi gli passate engine, PyARO, carica i dati usando ARO. ma in passato la gente spesso caricava i dati in arrow solo per poi chiamare toPandas e poi usarli in pandas, ok? E in quel caso io avevo bisogno di 2 librerie per poi magari eseguire, che ne so, un'aggregazione sui dati. A quel punto forse conviene dire, cioè già PyArrow per caricare i dati, tanto vale che uso quella per eseguire anche l'aggregazione, i filtri, le robe, eccetera. Ha un livello di funzionalità che di solito è sufficiente per, diciamo, il 70% dei casi d'uso. Certo, Pandas si è evoluto nel corso di ormai anni e quindi ha implementato funzionalità anche per i più interni casi d'uso, però vuol dire anche che ha un'interfaccia più complicata. Di solito se voi volete fare qualcosa in Pandas trovate almeno 5 modi di fare la stessa identica cosa. In Arrow è più facile. Però sicuramente è più orientato a chi deve scrivere applicazioni che userete.
Allora, posso usare Arrow per sostituire completamente Hadoop? Questo secondo me domanda... c'è una differenza?
Con troppa fatica, oserei dire. No, cioè, teoricamente puoi farlo, non ha alcun senso reimplementare l'intero stack di Hadoop. Certo, potresti implementare un sistema che computa distribuito su più nodi usando Asero, usa Flight per scambiarsi dati e tutto quello che volete, però stiamo andando molto fuori da quello che probabilmente volete fare voi in prima persona su Arrow. Probabilmente c'è qualcuno là fuori che se lo sta implementando come prodotto e voi prendete e lo usate. Non è che vi consiglio di tornare in azienda domani e dire sostituiamo Hadoop con Arrow, perché sarebbe 5 anni di lavoro. Ballista non è proprio la stessa cosa, è un orchestratore di query, però è ancora molto lontano da tutto quello che vi dà Hadoop come gestione del cluster. Okay?
Allora, sempre proviamo a scarrellare. Quale può essere una roadmap di transizione per un progetto che ha sempre usato Pandas per manipolare i dati?
La mia domanda è perché dovreste cambiare. Se Pandas sta internamente piano piano approcciandosi ad Arrow e usando Arrow per la computazione dei dati, almeno per ora non hanno ancora chiara quale sarà la roadmap definitiva, però si stanno muovendo in quella direzione. A quel punto a voi cosa vi interessa? Sia che usiate Pandas sia che usate PyArrow, alla fin fine già ora per le stringhe usate Arrow, cioè perché l'implementazione in NumPy delle stringhe, dicevamo prima, non è proprio la migliore, quindi Pandas supporta Arrow come implementazione.
Allora, sempre su comparison di prodotti, è più veloce fare analisi dati su PyArrow Tables o in Polars? E poi, quanto è più veloce Pandas ora che è basato su PyArrow?
Due domande molto differenti. In alcuni casi Arrow risulta più veloce di le equivalenti operazioni su Polars, ma sono casi specifici. Nella maggior parte dei casi Polars risulta lievemente più efficiente. Oserei dire una differenza di solito che non noti, per cui se sei già un utente Polars ti conviene restare su Polars, perché dentro Polars è basato su Arrow di nuovo. Quindi siamo sempre
altra domanda, Polars nello stack si posiziona dove quindi rispetto a quello che hai presentato
allo
fino
stesso
adesso?
livello di Pandas o IBIS. Prima vi ho menzionato IBIS. IBIS è vedetelo come un Pandas agnostico a dove poi l'operazione computazionale viene effettivamente eseguita. Quindi voi costruite tutta la vostra pipeline di operazioni all'interno di IBIS, gli dice eseguitela sul backend che ho scelto e quello ve la esegue su Pandas, su DuckDB, su Asero, su dove cavolo volete, su Postgres. Ok, quindi
Qual è la differenza fra un array di stringhe e un array categorico?
In termini di implementazione o di concettuali? In termini di implementazione sono molto diversi, perché l'array categorico solitamente è implementato su dei numeri, è un semplice array di interi a cui a ogni numero io assegno una rappresentazione testuale che è la categoria, mentre invece l'array di stringhe è un array con il buffer di memoria delle stringhe a cui è associato un array di posizioni che mi dice dove trovo ogni stringa separata, e quindi l'implementazione sottostante è molto diversa. Anche a livello logico capisco che uno può dire mi uso un array di stringhe per rappresentare le mie categorie, ma se posso farlo con un intero, se ho 8 categorie, che ne so, capito? Posso usare un byte per rappresentarle, perché devo metterle in, non lo so, 200 byte se il nome della categoria è lunghissimo.
Ultima domanda, che significa che PyArrow non copia i dati quando converte a NumPy, quando fa to NumPy?
Significa esattamente quello, che i dati sono in un buffer allineato che NumPy capisce e quindi gli passa il puntatore e dice fai te, finita. Cioè ci sono alcuni tipi di dati che vi dicevo hanno bisogno di conversione. Per esempio mi sembra il supporto ai decimal deve essere convertito, il supporto alle stringhe deve essere totalmente convertito, però per la maggior parte dei dati interi di qualsiasi dimensione, floating point o cose del genere, la zona di memoria è condivisa, sia Arrow che NumPy accendono allo stesso identico indirizzo in memoria e tutti e due lavorano con quel dato.
È possibile sostituire completamente gRPC con Arrow? Domanda, diciamo, dal contesto.
Esatto, nel senso che in Flight, che è basato su gRPC, io posso implementare dei metodi custom, ma se il vostro unico scopo è implementarvi un API basato su gRPC, cosa vi serve Flight? Sì, posso. Alla fin fine FlySQL fa qualcosa di molto simile. Usa Flight per trasmettere i dati e a Flight aggiunge tutta una serie di metodi custom che servono a gestire l'interazione col database. Però lì è perché c'è lo specifico bisogno di usare Arrow per la trasmissione dei dati. Se voi dovete implementare un API in un qualsiasi server, non credo abbia senso appoggiarvi a Flight.
Puoi dirci qualcosa di più sulla parallelizzazione via GPU su Arrow?
Questa è una bellissima domanda. È qualcosa che in Arrow è ancora molto prematuro, il supporto alle GPU in generale, ma esattamente in questo momento il team di sviluppo sta lavorando su supportare la rappresentazione di dati in formato Arrow all'interno della memoria della GPU e scambiare questi dati in modo tale che il ricevente dei dati sappia se sono all'interno della memoria di una GPU, di una CPU, di un FPGA, dove deve andare a cercare questi dati. Per cui piano piano sta venendo implementato il supporto alle GPU. Non è tra gli obiettivi di Arrow, almeno per il momento, offrire uno stack computazionale basato sulla GPU. Potete prendervi QDF e QDF capisce i dati Arrow. Nel momento in cui sarà finito il lavoro di permettere ai dati Arrow di essere interamente alla GPU, se voi usate QDF computate in GPU sui dati di Arrow.
Ultima domanda, qual è la tua esperienza personale con questa libreria e come contribuisci e se contribuisci al progetto Arrow?
Contribuisco al progetto come committer prevalentemente sulla parte Python, anche se in verità spesso e volentieri ho dovuto...
Quella Java?
Quella Java mi è proprio...
Io ho visto qualche PR in C++.
Sì, esatto, stavo dicendo, purtroppo Arrow è implementato all'80% in C++, quindi dire Python è falso, in verità l'80% del lavoro fa in C++ e in Python fa il binding in pratica, in Cython per lo più, Python ce n'è molto poco, e comunque sì, mi è anche toccato mettere mano alla libreria Java, tu che prendi per il culo.
Ma lui contribuisce a...
Io sono maintainer di un progetto Java da 12 anni.
Ecco.
È auto shame, insomma. E ancora lo usano, ma siete matti, ragazzi. Basta.
Chiediti perché non ne esce fuori, a chi la rifila la sola.
No, open source.
Esatto.
Ragazzi, un grande applauso per Mole Molina, Alex.